Hello. Today we are talking about the paper Causal Explanation from Mild Cognitive Impairment Progression using Graph Neural Networks, which is published in a BIBM 2024 in the workshop of Artificial Intelligence Techniques for Biomedicine and Healthcare. Thanks to all authors, Muskan Garg, Jingyi Liu, Maria Vasilaki, Jennifer Sauer, Ronald Peterson, and Sung-Hwan Son. I'm Arman and I'm presenting this study for you. So the study aims in this work are explore the potential causal explanation of mild cognitive impairment progression by utilization of temporal patient data, including chronic diseases, biomarkers, and genetic information into a graph structure to capture the causal relationships between variables. And also we wanted to explore the sex-specific differences in MCI progression using GNN-based causal explanations, so we can reveal the sex-dependent pathways in cognitive decline. The data we are using here is the Mayo Clinic study of aging, which is exactly a population-based cohort focused on understanding cognitive aging. It has detailed cognitive assessments on participants in 15-month visits in 10 years that this data has been labeled for diagnosis of the stage. For example, if a patient is now in MCI stage, or it's progressed into dementia, or it's been cured to cognitive situation. These labeling have been made by a committee consisting of 3 evaluators based on established criteria. The studied variables here are chronic diseases, sex, age, genotype, and biomarkers. In this paper, we proposed a novel approach for understanding mild cognitive impairment progression by explainable graph neural networks. As you can see here, we gathered MCSA data, which is the study of the variables that we have in every visit for patients. And also we have another data set named RepID data, which is the exact data set for different visits for chronic diseases for these patients. So two challenges at first was this data should be not null, shouldn't have not values, meaning that the missing data should be imputed. And also, we should have merged these two data sets in different ways, because both of them are temporal, but they are from different settings. So we had to merge and sort them in temporal-based nature data sets. So we preprocessed this data set into a new one. And then we had to make a graph and construct a graph based on this preprocessed data set. So we consider variables as nodes, variable mutual information as edges, meaning that each two variables has a mutual information value, and we consider that as edge, which is a value between 0 and 1 in a scale way. And also MCI conversion class as node label, and variable values as node feature tables that we train GNNs based on that. I will talk about GNNs. And the graph structured data makes out of it, and then we train the graph neural networks on that. So this training can be evaluated by different ways. Like we have different structures for graph neural networks. One of them is temporal graph convolutional networks, and also the graph neural networks with attentions, and also the graph sage model. But we can evaluate them with parameter tuning and make them better. The next stage is explaining these GNNs. So in the literature, we have GNN explainer method, guided backpropagation method, integrated explainer, and RC explainer. But there is a paper named GNN causal explainer, or CXGNN, that specifically we want to use the results of that. But we are using the other explanation methods as baseline for this. And then at the end, we evaluate this explanation by 3 specific evaluation metrics: accuracy, stability of results, and faithfulness of results. So what are graph neural networks? Graph neural networks are the neural networks trained on graph data, meaning in each graph, we have node that has node labels and node features, and we have edges that had edge labels. And also the graph itself has a label that we call that graph label. So when you train neural networks for specific tasks. Uh, it can give you the information over different input of data. For example, we have a task named node classification. If you want to categorize the or classify the label of the node in different stages and different time, so you can do this task, or you can do the graph classification, which is classifying the label of the graph. Now we want to study what is the MCI to dementia, meaning the progression of MCI in a causal way. So we have this diagram you're seeing now. For example, we have the label Y, which is MCI, or staying at MCI, or MCI to dementia. And we have some variables we are studying, like chronic diseases, biomarkers, and we have some variables that we are not studying. They are Z, like economical, I don't know, like drugs, smoking, something like that, that they can maybe affect this process, and we call them Z. So these variables, all of them can be measured. For example, the chronic diseases, we have the values. They are, all of them are in X. Or if this specific patient is in MCI stage or MCI to dementia, we can measure that. And also the variables that we don't have this in this data set, they can be measured too. But we don't know exact effect of these variables on each other, and we don't know the effect of other variables on these variables. So we call that latent space, which is the measurement that we are not able to observe in the real world, and we show that by U. So each of these variables, dependence and independence, they have U. For example, U of Z, or the latent space, is a latent space for variables that are not considered in our study. U of X is the latent space that are for the variables that we considered in this study, and we know them. And now we have do of X, meaning that it's the intervention, meaning that when you want to change the value, for example, if a patient now has a specific chronic disease, if we want to intervene this input, we can change that to not having this chronic disease, meaning that we intervene, and now we can study what would be the effect of not having that specific chronic disease in our study. And then we can train a model to identify the causal subgraph on this observable and latent space or unobserved space of data. The main method of explainer we are using here is the SEEX-GENER. This method is a constructive method that grabs each node and tries to study the effects of all the related nodes on that specific node. For example, here we have a complete graph. We choose the green node here, and we want to study the effects of other nodes on that. And we see that these blue nodes are the first neighborhood of this node, which are directly linked to the target node, the green node or reference node. Also, these red nodes are the second neighborhood, meaning that they are not directly linked to the target node, but they are linked to the nodes in the first neighborhood. In the causal explanation, we know that we can build a SCM on that, and also which is a structural causal model given the input. But in this paper, it's been proved that you can estimate it really exact in theoretical way, and it's been proved to be worked on the real-world data sets. How do we represent the patients in this graph? In this graph, we have variable influence graph, that the red nodes are the nodes that are more important for MCI stay. The blue nodes are the nodes that are more effective and important on the label MCI to normal. And the green nodes are the nodes that are more important for MCI to dementia. So consider the data we have for this specific study. We made this graph, and variables are nodes, and the links between variables are the mutual information. So if you see a link between two variables, means that they are having like important dependence between each other. And if there's no, they're not that much important. Their dependency is not that much important according to the data set we have. This slide, we are seeing the results of graph neural networks predictions in temporal dataset. We see that temporal graph convolutional networks and the graph neural networks with attention networks are working better in accuracy, F1 score, and the area under curve, and also the precision. In this slide, we can see the results for graph neural networks explanation. And the first column, you can see that 6th gen outperformed the other baselines, meaning that the best explanation is stability, GES, which means that how much similar are the explanation for a given graph and its perturbed counterpart. The second column, GEA, shows the accuracy. Again, the best one is achieved by 6th gen. And the third column, GEF, which is the faithfulness, the least unfaithfulness of the explanation, which means the distance between probability distribution of the mask constructed subgraph and original one, is also achieved by 6th gen. In this slide, we answer the second research question, which was the role of sex in transition from MCI to normal. So consider the causal subgraph when the target node is node sex, and we want to study the effects of all the other variables on this node. It turned out that 2 chronic diseases, coronary artery disease and osteoporosis, are in this first neighborhood, and also the GFAP, which is the glial fibrillary acidic protein biomarker, is also in this first neighborhood. And we have NFL, TAU, CKD, and STR, which you can find them in the paper. They are in the second neighborhood when the sex is the target node, meaning that the first neighbors are the cause, are the potential cause for that. And also second neighborhood nodes can be too. And you can see the expressivity measure here, which gives us the amount of information each node can give us in the causal explanation. The higher it is, the closer it is to 1, meaning that it's more informative when you're studying the cause and effect for the other nodes. And you can see that all these nodes relatively to the sex, they have good amount of expressivity measure. So according to this causal subgraph, if you change the value of the nodes in the first neighborhood, the value of the target node might be changed too. This is the intervention in causal diagrams. And you understand that this intervention gives us more information about the cause and effect. So in summary, our approach has the potential for personalized risk assessment in MCI progression, guiding more targeted intervention. And we found out that sex may play a non-moderating role in MCI progression rather than a direct indicator. The limitations in this study were generalizability of the findings due to using only Midwestern population, and also the potential for unmeasured confounders, which we talked about at first. The future work in this direction can be identifying the underlying causal DAG of the study cohort. The causal DAG means the causal diagram, and also understanding the causes of MCI stages transition by text data by the state-of-the-art causal language models. Thanks for your attention. Please scan this QR code for more information and code.